we come to probably the most important application of integration, that is using integration area of a region between two graphs expressed as an integral. So first, let's define what the area between two graphs is. The area of a function f and g defined on this integral AB, and f of x is less than equal to g of x for all x in this interval AB. Then let S be those points, basically the ordinate set, but not ordinate set, but let's define x and y such that f of x is less than equal to y is less than equal to g of x. That means y is between all those points between g of x and f of x. And well, as we define, x is between a and b for all. Then this set S is called the region between f and g, between the graphs f and g. So there can probably be two types. One is like this, another like that. This is one. It can also be under. This is for non-negative function. And there can also be one function which is like this, and another here. This also. Now we come to a theorem in describing the above mentioned concept. We have, okay, let me just write it down, then I'll state it. So there's f and g. They are integrable, and a and b and f less than g. In the region is between the graphs of measure. This is what we know from the concept. We need to define what the test is, difference between the ordinate set. And what is that measure of the ordinate set area? Well, that is g of x minus f of x. And that's the function. And the difference of functions, the function, and then you integrate that function. So let's prove this for a non-negative function. That is both f and g are about 0 for all x in this interval. So first we say f is an ordinate set. Let x be such that for all x in that interval and for all y for that function except the graph of that itself. So this is f except this graph, everything under it except this line. So that is the ordinate set of f. First, the area of that graph, as you know, is 0. So I don't understand why exactly they stated it explicitly. But and then the ordinate set of G itself. These are just definitions. Now we know that Any function that is integrable has an ordinate set, and that ordinate set is measurable by that integral. So f and g are both measurable. Now, since f and g is measurable, s equals g minus f, because that is the real. And s is also measurable as f is less than g. So now we have a of f equals a of g minus a of f. But we know that the area of the ordinate set is just its integral, right? And we can know this by additivity in the same. We can write this as just proof it for a non-negative function f and g. Say f and g are non-negative for one function. Okay. Well, we know that there exists some c number of the real number such that you can add that value to the non-negative function and create a zero. Say, for example, bounded by this is least value in c. We have it become greater than or equal to 0, and every point shifts upward. So we have two non-negative functions, and we know that the area, say t is the area between f of x plus c plus g of x plus c. And since they are non-negative, we can just find the area between them, as stated before. And this gives us this equation or this integral, and this is congruent to s. And by definition of congruent to s, a of t is then equal to a of s, which implies a of t is measurable also. I mean, a of s then a of s is measurable, is very equal, and so a of s equal to a of t is equal to for a general function. So now we come hands-on in some worked examples, or about 6 to 7 worked examples with a little bit of theorem sprinkled in between. So let's get to the first example. So we have to compute the area in the graph f and g such that f of x equal to x, f minus 2, and g of x equal to. At first glance, it seems that this integral 0 to f of x is taken g of x, but it's always better to graph it out because it is greater over coming to. First, let's find out that. So x to x minus x, right? We don't know. Just say we want to find points where the area is between them. So we just subtract these two. So the integral also is 0. And then we know that those points are intersecting. Then So what did I do? 2 by 2 x. And with that x square minus 2x, we take x common, we get x minus 2 minus 1 by 2 is equal to 0. So x is equal to 0 at one point, and the other point is x equal to 1 by 2 is 0. So x equals to 4 by 2. But uh, uh, so we just say x equal to 1 as part of 1. We just find out that, which is read. So that is 1 to 1 minus 2 is equal to minus 1. So clearly this is a negative function. G of 1 is 1 by 2. So obviously g of x is greater. So the function like that, the constant function. And then let's see. So if you want to be accurate, you can just find the derivative and find out which point it turns. But in this case, the area is 1 now. And g of x is greater than f of x. So I'll find the area between on the interval 0 to 2. We go ahead and find our interval. And we know 0 to 2 x by 2 minus x plus 2x with minus x into so type 2 x minus x square, which gives us 5 by 4 1 minus 0 3 x equals 0 1. Just 0 3. Then we come to example 3. So we have two functions. No, wait, this is example 2. So say f of x is equal to x and g of x equals to x cubed by 4. So let's just graph them out. So this is our standard x equal to y function. And we know the cube function increases. Let's we can just draw a better function. So and if you scale it, you just shrink it towards increase it. If you increase this value, then this decreases. But if you increase the lower value, then it expands. So let's find these points. Because here g of x is greater, and here f of x is greater. So we find those points. So let's go x minus 60 by 4 equals 0. We take x out. We have 1 minus x square by 4. Now this is kind of familiar. We can again factorize this as a square minus b square. So we get a plus b into a minus b. So x is equal to 0. That's one point where the area is 0. And x is equal to minus 2. Minus 2 is equal to 2. So we come back. So it is minus 2 is plus 2. So it's minus 2 to 0 and then 0 to 2. But then our interval is minus 1. So following that connection, minus 1, g of x is x cubed by 4 minus 1. And then from 0 to 2, x minus x cubed by 4. We integrate it, we get x to the power 4 by 4, which is 16 minus x squared by 2 from minus 1 to 0, and x squared by 2 minus the power 4 by 6 from 2 to 0. So this is 0 minus 1, which is 1 itself, and also this minus into minus, so we just put that here, right? Minus 1 squared by 2. Simplify this here itself, we get minus 16 plus minus 1 by 2, but then you get the minus inside 1 by 2. And then we also get 4 by 2 minus 16 by 16. And we make this into the common denominator. So this becomes 8, this becomes 8, this becomes 4 into 8, this becomes 16, and 16 by 16. You get minus 1 by 16 plus 8 by 16 plus 52 by 16 and by 16. This is 16. This is 24, 24, 33. Now we come to example 3. That is area of circular disk. So area circular disk with radius r is the set of points inside or on the boundary of circle with radius r. Now that area is equal to the area between two graphs are congruent. That means that area is equal to this area and with respect to this between two functions f and g defined on the interval minus r to r with f of x equals minus r for x squared and g of x equal to r squared minus x squared. Now these are piecewise monotonic functions. So hence they are integral. I don't know if I'm pronouncing that right. So then let's go ahead. But also g of x equal to minus f of x. So now we find the area from minus r to r, g of x minus f of x dx, which will be equal to 2 g of x. Now say the area of this is a function of r. I mean, yeah. Now say a of 1 that is equal to this is 1. And this say This is equal to pi. Okay. Now we have r is equal to 2 minus r of x by dx. Or wait, an easier way to do it, just keep the g of x. But then we have r, then also we r times minus 1, 1 we divided by r, the expansion or contraction in the into, and you get g of r, which is equal to 2r minus 1 to 1 r square minus r square x square. We take the r out. Alright. And this therefore is equal to r square is equal to r square area of unit radius circle, which is equal to 5 r square. So we define pi to be a number such that it is the area of a unit disk. Now we come to some linear algebra, or basically the intervals. So say we have set such that there is some xy and a is equal to x equal to b for some interval, and y is equal to f. This is the graph itself, essentially. Say y equals x, we have that. So basically, a similarity transformation is you just scale it. If k equals 0, for example, you multiply ks, so it becomes xy such that 2a less than equal to x less than equal to b, because you're multiplying each of x into 2. And y will technically be the same because we're using the same x. So it becomes twice that anyways. Not twice that, some value of that. Say for another example, let me just show you a graph. So in this graph, you can see first it's at 0.5, and then as you multiply it, it becomes x equals 1, and it becomes 1. So what that similarity transformation does is the original distance from this point through the same line to the origin is doubled. So you have here, it goes here, through the same line you double it, you come here, and then you come here again, and that is the similarity transformation for x equal greater than 0. But through that same line of x is less than 0, say you have an original point, say 2, for that function y equals f, right? So you divide that by 2, so the x becomes 1. And through that same line from the origin, doesn't have to be necessarily y equals x, it can be some random function like this itself. To that same line through that point, it becomes half that. So for example, if it's going all the way here from the origin to this point, it becomes half that. So that is what a similarity transformation does. The distance from the origin through a straight line reduces, so expands and contracts. So that is what expansion or contraction means. So next we come to another example, which describes the behavior of the area of an ordinate set under the similarity transformation. Behavior of the area of an ordinate set under the similarity transformation. So say the function f on this interval and this integrable. I don't know if I'm pronouncing that right, but on into, okay, and S is the ordinate set of F. And we know A of S exists and is measurable because of this. And we apply similarity transformation through G of S on this interval. Okay. So now a point on G of X, that is XY, would have to be on F such that that same point. Think about it. So the similarity transformation K of X, so that is equal to Y. But that same point would have to be Y of K, and F of X by K, because it has to be on a same point. This is just for clarity. So for Y is G of X. So this has the following relation. So now that aside, so this area of this expanded or contracted one is the integral from K to KB. So, but we also know that this is equal to this from above relation from here. Then again, using the expansion and contraction interval theorem, we get this. And this is the area of S. So area of Ks is K times. So the area of the expanded function is equal to K square times the area of the original one. So next we come to example 5, that is calculation of an integral 0 to A x to the power 1 by n. In the book it's actually x to the power 1 by 2, but this is generalized and we can prove next theorem also. So here A is greater than 0 and n is a positive number of positive integers. Okay, so now let's just draw a graph of x to the power 1 by n. It's an increasing function. So it so say for example I'll take it. Okay, wait. So now this point is A. So A comma A to the power 1 by n. So you take a y equal to A to the power 1 by n. So that is our standard. So now say we want to calculate this area, A of S. So A of S is equal to, well, it's integral. It's that function. But say we don't have any specific formula on how to do this, but we can use our knowledge of area. So say this area is equal to A to the power AT. So AT plus AS is equal to what? This is A into height. So for 1 by n, which is equal to A plus 1. And you can just see a graph to get a clear visual. So this is our function. We take x to the power 1 by 2. So this is a function. So we take here, say a is equal to 4, and then y is equal to a to the power 1 by n. Over here 1 by 2. So 4 to the power 1 by 2, which is 2. So y equals 2. So this is the rectangle we're interested in. Let me just, yeah, so you can see this rectangle here, this with the blue line, that is our area which we are concerned with this respective example. So now we define a function which we will see later in the example, g of y, and let g of y be such a function on y from the interval 0 to a to the power 1 by n. Over here 4 to the power 1 by 2, which is x equals y to the power 2. So when we plug that in, you can see we get this function. So from the 0 to a to the power 1 by 2, which is 2. So this portion here is a to the area of AT. So as we saw, so A of S is equal to a to the power 1 plus 1 minus A of T. That is this portion here. And as we define, so T is the coordinate set of a function G defined on Y, the function of Y. So Y is a number from 0 to a to the power 1 by n. And G of Y is equal to y to the power n. So A of T is equal to 0 to a to the power 1 by n yn dy, which is equal to y on. So now we come to a function of s equal to 1 by n minus a, which is equal to, so equal to, or this can also be written as, okay, that doesn't matter. So now similarly, a greater than 0, greater than 0, s to the power 1 by n. So we know so then what we proved, now we just stated formally theorem 2.2, a positive, b positive, n is a positive integer. We have integration of x to the power 1 by n from a to b is equal to this.